What happens when
People's
a
noise.
solid
That
when you use solid, that is transparent or energy, it's called the solid to vibrate. When you vibrate strongly, you lose time. That
You want to use laptop, Abi?
Give me just say she will be decent. Now come every mount. Remember you start from
300.
I'll go tell her that you download shooting game.
Good morning, class.
Good morning, sir.
Good morning, sir.
Good
morning, sir.
Thank you. Today we want to continue with the thermal physics class. We're looking at specific heat capacity, and after the class. So if you need to boil a kettle of water, generally, you will need to heat the kettle as usual, filled with water, and heat will be absorbed by the water to increase the temperature. This is a normal thing, and but if you want to increase the temperature by just 1 degree, you want to increase the temperature of 1 kilogram of water by 1 degree, then certain amount of heat must be absorbed. Hello, I'm already in class. I'm already teaching. So certain amount of heat must be absorbed by the water. And this heat is what is called the specific heat capacity. The specific heat capacity. Now, specific heat capacity is the amount of heat needed to increase the temperature of a mass of 1 kilogram by 1 degree. Temperature of mass of 1 kilogram by 1 degree. That gives us the specific heat capacity of the substance. And the unit is joule per kilogram per Kelvin, or joule per kilogram per degrees Celsius, depending on the unit you are working with. For instance, for that of water, the specific heat capacity is 4,200 joule per kilogram per Kelvin, while that of iron is 452 joule per kilogram per Kelvin. From these two values, you can see that the swimming capacity of water is greater than that of iron. The implication there is that iron will get hotter faster, the minimum heat compared to that of water. So water will require up to 4,200 joule to be able to raise its temperature by 1. But iron will just require 452 joule to be able to raise its temperature by 1 degree. So the implication there is that water requires more heat to raise the temperature by 1 degree. Another way of looking at it is that iron is a better conductor of heat. So it will require just 452 joule compared to water that require 4,200 joule. So this shows that it is easier for an iron to get hot, as I said, compared with water. Now, specific heat capacity, again, we use small c to represent specific heat capacity. And it can be calculated from the amount of heat supplied. Amount of heat supplied is represented by Q, capital Q, and the mass of the water is M. So specific capacity small c is Q divided by M times the change in temperature, which is theta. So C is Q over M theta. In other words, quantity of heat can also be calculated by saying Q is equal to MC theta. This is the formula we're all aware of, very familiar with us at all levels. Now, there are also some certain substances that exist in phases. They have the solid phase, the liquid phase, and the gaseous state. Just like water. Water exists as solid, liquid, or gas. So the amount of heat required to change the phase of a substance will also depend on the mass and again, the type of material that makes up the substance. For instance, a small ice cube will melt quickly, but a large block of ice melts very slowly. Like 100 joule of heat energy can melt a large amount of wax, but same amount of heat can only melt a small amount of another substance, for instance, copper. So all these are, as we said, the amount of heat will depend on the mass of the substance and the type of materials that makes up the substance. So the specific heat, this leads us now to specific latent heat. The specific latent heat of a substance is the amount of heat that is required to change the phase of 1 kilogram of the substance at a constant temperature. That's without change in temperature. We use L to represent the specific latent heat, and that gives specific latent heat L would be Q, which is quantity of heat divided by M, the mass of the substance. So as I said, Q is the quantity of heat or the latent heat absorbed or released by the substance. M is the mass of the substance. Now the unit of specific latent heat from that formula, L is Q over M, will be joule per kilogram. If Q is measured in joule, mass is measured in kilogram. So Q over M, therefore the unit will be joule per kilogram. That's joule over kilogram. I would say joule times kilogram raised to power -1. It means that's joule per kilogram or joule times kilogram raised to power -1. So As I said, the latent heat absorbed or released when a substance of mass m changes from one phase to another is represented by L. As we have seen that L is Q over M. And again, so the latent heat of fusion of substance is the amount of heat required to change 1 kg of the substance from the solid phase to its liquid state. So fusion is changing from solid phase to liquid phase, while that of vaporization is changing from liquid to gaseous state. So we have only two types of latent heat of fusion and latent heat of vaporization. As you can see now, the specific latent heat of fusion of a substance is usually smaller than the latent heat of vaporization. If you ask that question, why is it smaller? Why is the latent heat of fusion of a substance usually smaller than its latent heat of vaporization? The reason is that there is an extra work to be done against atmospheric pressure during the change of phase from liquid to gas. So that's the reason why you have to that's the reason why that of fusion is smaller than that of vaporization. Should take note of this. Now, we move to gas laws. I don't think there's any question on that, on specific heat or specific latent heat, because they're all very familiar. So the only thing you need to do is to try and solve some questions on that. These are all O-level. These are what we have done before while we are preparing for our YEC or when we are preparing for JAM. So we're just trying to remind ourselves. Now, gas laws too. Here we're examining 3 types of gas laws, which are Boyle's law, Charles' law, and pressure law. And before then, we look at the factors that affect a gas. They include the quantity of the gas, which the quantity of the gas is measured in moles. So N in moles, the temperature of the gas, capital T, which is in Kelvin. But if it is in Celsius, you have to add 273 so as to convert it to Kelvin. The pressure also of a gas P, which is in Pascal, and the volume of the gas V, which is centimeter cube or cubic meter, whatever. But it's in SI unit, you call it centimeter cube. So these are the 4 factors that will affect a given gas. So based on that, you will be able to look at these 3 laws: Boyle's law, Charles' law, and pressure law. Boyle's law says that if the temperature remains constant, the volume of a gas is inversely proportional to the absolute pressure. So in other words, P1 V1 is equal to P2 V2. As you can see from that formula or from the figure here, when V is 1.0 liter, pressure is 100 millimeter mercury. And now when the pressure is reduced to 0.5 liter, pressure is now increased to 200 millimeter mercury. So pressure is inversely proportional to volume. That's why you see this type of curve as the relationship between V and P. So that's the inverse relationship. V is inversely proportional to P. So the Boyle's law says P1 V1 is equals to P2 V2. An example here, the volume of the lungs is measured by the volume of air exhaled or inhaled. Exhaled, that one you give out, and inhaled, the one you breathe in. So if the volume is 2,400 liters during exhalation and the pressure is 101.7 kilopascal, And the pressure during inhalation is 101.01 kilopascal. What is the volume of the lungs during inhalation? So these are just the same, applying that formula of P1 V1, P2 V2, and you substitute the value. The unknown one there is the V1, the volume during inhalation is what we are looking for. That will be V1. Our V2 is 2400 liters, which is also 2.4 in kilos. That's times 10⁻³ liters. So when you substitute these values, you can easily find our V1, which now is 2,416 liters. 2,416 liters. Says, who is raising his hand? What's the problem? Tijani, what's the problem?
Good morning, sir.
Yeah.
This question, can we be asked to leave our answer in centimeter cube? This pressure and this
You don't have to ask me
volume.
that. Anything you see in the question, you answer it. You can be asked the question in any way. You as a physics student or as a science student should know that there must be what? You have to convert any unit that is not in SI unit. Or if every other thing is in any other, there must be uniformity in the units. You can't solve some parameters in maybe in gram and others in kilonewton. No, it's either all of them are the same unit, kilogram, newton, or meter. If they are in cm, it converts so that every other thing will be in SI unit. So why are you asking at this level again whether you have to convert? You have to convert if need be. But when you see that the units are uniform, all of them, all true, then you solve in the appropriate unit. Don't need to ask such a question at this level. That is what part of your training, that you look at the unit of any question, know whether to convert or not to convert. If they are not in uniform, I mean, all the parameters given, they don't have a uniform unit as per whether they are in SI unit or in other forms of units. Fine.
We used to give
You have
Lola
to
milk
make it.
today. Chai, I made my pinna again. I made my pinna again.
That's the problem. When you interrupt, other people will have be saying something different. I don't know what this person is talking about. So we move on. Then Charles' law. Charles' law states that if the pressure remains constant, the volume of a given mass of gas is directly proportional to the absolute temperature. Absolute temperature. So if you
Yes.
look at the graph here, V is directly proportional to temperature. Remember, the temperature here must be in absolute temperature, not in degrees Celsius, not in Fahrenheit, but in absolute, that's Kelvin scale. V is proportional to K. Sorry, V is proportional to T. There will be a direct proportionality. That's a straight line there. So as you can see here, it means that V1 over T1 is equal to V2 over T2. That is our Charles law. V1 over T1 is equal to V2 over V2. That is V is proportional to the absolute temperature. For instance, in this case now, you see the volume is measured in centimeter cube. So if the volume is in centimeter cube here, and you decide to solve it with centimeter cube, that means your answer will also be, the final volume will also be in centimeter cube. So there will be uniformity there. But if they ask you now to leave your answer in meter cube, the implication is that when you solve here, you have to convert, or you convert here directly before solving. So the initial, I've muted this. I don't know why. If I mute, some people will go and unmute. So, from the information given, the initial volume is V1, 30 centimeter cube, final volume V2, which is what we are looking for. And the temperature, as you know, must be in Kelvin scale. The temperature must be in Kelvin scale. So that temperature there, which is 27 degrees Celsius, that's the T1. You must add 273 to it, and that gives off 300 Kelvin. And the other one, 27 degrees Celsius, you also add 273 to it, that gives off 400 Kelvin. So when you now substitute into the formula, V1 over T1 is equal to V2 over T2. The only unknown there is V2. You make V2 the subject of the formula and get it to be, that's a 3.0 times 400 divided by, 30 times 400 divided by 300. That gives us 40 centimeter cube. So the final volume of the balloon is 40 centimeter cube. Please check, this is 30, not 3.0. This substitution you made there is 30, not 3.0. Now, the pressure law. The relationship between temperature and pressure, this was investigated by Galuskas law. Galuska, sometimes it's called Galuskas law. That pressure, so the implication here is that pressure law is also known as Galuskas law, as I said before. Pressure law states that if the volume remains constant, the pressure of a given mass of gas is directly proportional to the absolute temperature. So P is proportional to the absolute temperature. P is proportional to capital T. So when you remove the proportionality, you introduce a constant. P is equal to KT. So where K is a constant. In other words, you can state the Galuskas law or pressure law to be P1 over T1 is equal to P2 over T2. As you can see, there's a relationship, direct relationship, straight line between pressure and temperature, absolute temperature, as you can have it there. So that is pressure law for you. P1 over T1 is equal to P2 over T2. As an example, the pressure of a car tire is 22 kilopascal at 30 degrees Celsius. After a long journey, the pressure has increased to 25 kilopascal. What is the final temperature of air in the tire after the journey, assuming the volume of the tire remained unchanged? So this was just for you now to substitute the values given. Just write out the given values. P1 is 22 kilopascal. T1 is 30 degrees Celsius, but this time around, you have to convert it to absolute scale. So 30 plus 273. That will give us 303. Again, P2 is given as 25 kilopascal. So you have to look for T2. So from P1 over T1 is equal to P2 over T2. You make T2 the formula, and now substitute the values. You can now obtain T2. T2 was obtained to be 33.23 Kelvin. So you can convert it back to degrees Celsius by subtracting 273. When you subtract 273, you are now left with 71.32, but now it will be in degrees Celsius. 71.32 degrees Celsius. So these are very simple ways of doing this. Now you can also combine the three laws. The three laws can be combined to have P1 V1 over T1 is equal to P2 V2 over T2. You go to P3 V3 over T3. Or you just straight away, you say PV over T is equal to a constant. Just as you have here, P times V over T is equal to a constant. This is the combination of the three laws. So at the end of the day, you can always get one parameter out of the four that's when three parameters are given. Then the unknown can always be looked out for from this expression. For instance, pure helium gas is admitted into a leaked roof cylinder containing a movable piston. The initial volume, pressure, and temperature of the gas are 15 liters, 2.0 atm, that's atmospheric pressure, and 300 Kelvin. If the volume is decreased to 12 liters and the pressure increased to 3.5 atm, find the final temperature of the gas. So just like saying P1 V1 over T1 is equal to P2 V2 over T2. So you look for T2. Or here we use P0 V0 over T1, depending. Yes, Chinedu, what's the problem? Chinedu, you can unmute yourself. Answer the question. Chinedu Charles. Chinedu, side, raise your hand. What's the problem?
Can you go to the previous slide?
So what's the problem? Yes, that's the previous slide. What's the problem?
And I'm okay, sir. No problem, sir.
So when you substitute the values of the parameters here, you can always find the unknown. So here T is the unknown. And we are seeing that it will give us 420 Kelvin straight away. So, but there's another way again to get the full loss together by the use of what you call the ideal gas law, the ideal gas equation. Now we have seen that PV is proportional to the number of mole and also proportional to the temperature, absolute temperature. PV is proportional. This is a sign of proportionality. That's something that looks like alpha. PV is proportional to the number of mole, which is small n, and also proportional to the absolute temperature. Now, if you remove a sign of proportionality, what happens? You introduce a constant. So, but the constant here now is R, capital R, and it is known as the universal gas constant. Universal gas constant, and it has a value which is 8.31 joule per mole per Kelvin. Joule per mole per Kelvin. So the ideal gas law, therefore, will now be PV is equals to nRT. nRT, where small n is the number of moles, R, capital R is the universal gas constant, and T is the temperature. P already you know is the pressure, and V is the volume. So that's the ideal gas law. Ideal gas law. There are many versions of this. You can also have NKT. In that situation, you are bringing in the Boltzmann constant and the Avogadro's number. So all these are another way of writing the ideal gas law. But here, let us restrict ourselves here that PV is nRT. Yes, Blessing, what's the problem?
Good morning, sir. Sir,
Yeah,
please,
go ahead.
in some textbooks, we have PV is equal to MRT. That means they're actually using the math.
I'm not hearing you well. I'm not hearing you well. Blessing.
Okay, so I said in some textbooks we have they usually put PV is equals to MRT, which means that now they are using the mass instead of the number of moles. Is that also
That mass
correct?
there may be the molar mass.
The
And
molar
that M,
mass.
yeah, that M will be you can relate it to this formula that you have here. If you look very well, that M has relationship with the number of mole. And also,
Okay, sir.
yeah, it has relationship with the number of moles.
No.
You should check
Okay,
that book
sir.
very well. Yes, it's
Okay, thank you,
consistent.
sir.
Yeah, it's consistent. Now let's look at an example. Blessing, are you still raising your hand or? Let's assume
Yes,
it's the
I'm
old
just
one. Okay, another example says a helium party balloon. Assume a helium party balloon assumed to be a perfect sphere has a radius of 18.0 centimeter. Then at room temperature, which is 20 degrees Celsius, its internal pressure is 1.05 atm. Find the number of moles of helium in the balloon and the mass of helium needed to inflate the balloon to these values. So first of all, we are not giving the volume of the balloon directly, but we can calculate the volume because we are giving the radius. So, and you know that the volume of a sphere is 4/3 pi r cube. 4/3 pi r cube. So we are giving the r, pi is a constant. You just substitute there. You can now get the volume of the sphere, which is 0.0244 meter cube. So after getting that, you can now find our temperature in absolute scale. So you now add 273 to the 20 degrees that we are giving here, 20 degrees Celsius, add 273, that will give us 293 Kelvin. Then the pressure was given in ATM, that atmospheric pressure, you have to convert to Pascal by multiplying by 10 raised to the power 5. That gives us 1.05 times 10 raised to the power 5 Pascal. So with that, you state our formula. PV is nRT. PV is nRT. From there, you can find the value of N. Make N the summation of the formula. So N is PV over RT. Already you know that our R, which is a universal gas constant, is 8.31 joule per mole per kilogram or whatever. So you substitute it and straight away you get your N, your number of moles. So here our number of moles is 1.052 moles. 1.052 moles. It's straightforward and simple.
That's a Monday.
Now, we can also look at kinetic theory of gases. Kinetic theory of gases. This you can get from different textbooks. But we have this summary of it here. That the kinetic molecular theory of gases are summarized under these four. One, that a gas is composed of molecules that are separated from each other by distances far greater than their own dimension. Their own dimension, we're talking about either their radius or their diameter. So a gas is composed of molecules that are separated from each other by distances far greater than their own dimension. So the molecules can be considered to be points. That is, they possess mass but have negligible volume. They possess mass but have negligible volume. In electricity too, we normally do what we call a point charge. Point charge. That's a charge that is very small compared to the separating distance. Just almost the same thing. When you say a point gas, a point mass, also in gravity, when you are looking at the gravitational constant or the force of gravity between two masses. So we will consider something like a 2-point masses. In electricity, we talk 2-point charges. So here again, we are talking about molecules acting like a point. There, we are looking at it in the sense that it possesses mass, but has negligible volume. Second theory here, or second summary of the theory, second point here, gas molecules are in constant motion in random direction, and they frequently collide with one another. And these collisions are what we call, there are different types of collisions. They are elastic, they are inelastic, but this one now is perfectly elastic. The collisions among the molecules are perfectly elastic. The third one says that gas molecules exert neither attractive nor repulsive forces on one another. They exert neither attractive nor repulsive forces on one another. And the fourth one says the average kinetic energy of the molecules is proportional to the temperature of the gas in Kelvin. The average kinetic energy of the molecules is proportional to the temperature of the gas in Kelvin. So any two gases at the same temperature will have the same average kinetic energy. So normally K is a half mu squared or mv squared. Remember, u and v, we normally use it to represent velocity. While u is the initial, v is the final. So Ke is half mu squared. So in summary, the kinetic molecular theory of gases assume the following: that the ideal gas molecules, one, they are constantly moving, that's constantly in motion. Two, they have negligible volume. Three, they have negligible intermolecular forces. Four, they undergo perfectly elastic collisions. And five, they have average kinetic energy, which is proportional to the ideal gas's absolute temperature. So these are the five assumptions of the ideal gas theory. The ideal gas molecule, they are assumed to be constantly moving, have negligible volume, have negligible intermolecular forces, undergo perfect elastic collision, and again, the kinetic energy is proportional to the ideal gas's absolute temperature. So that is how it is. So I think, let me give space for any question, because I want us to stop here. I have a faculty board of studies to attend. Faculty board, I have a meeting today, but at least we have covered what we need to cover for today or for this week. So we are not losing anything. So, but let me give space for answer. For question, Farouk Gani, what was the question?
Sir, please can you go to the previous slide? Slide 36.
Slide 36 is the
Yes, sir.
same thing as slide 37. The just as slide 37, we summarize it. And maybe we created the fifth one. We just
Thank
divided
you, sir.
one of the. Yes, what's the question?
That's all,
Is
sir.
there
That's all, sir.
Okay. Samuel. Samuel Arikawe, what's the problem?
From the kinetic theory of gases, you said gases are always in constant molecule, abi?
How can gas be constant molecule or constant motion?
In constant motion, do they always have energy to be in constant motion? Like, are they every time?
Are they, what will remove their energy? Yes, they have, unless when you now constant, if you tamper with their volume, we now have to apply one of those laws to know whether if you increase the volume, what happens to the temperature, what happens to
Thank you, sir.
the pressure, and all those things.
Okay, thank you, sir. I
Yeah,
understand.
Joanne.
Morning, sir.
Yeah, good morning.
Sir, please, can you explain what you meant by the molecules can be considered to be points again?
Okay, I just use the one we know with, I don't know, in physics again. Let me give you an example. When you have let's say two masses now. Two masses. Okay, let's use electricity now. Two charges. In electricity we have positive charge, negative charge, and you bring two charges together. They are separated by a distance. Now, those masses are called, those charges are called point charges if the dimension of those charges are small, very small, compared to what? The separating distance. I don't know if you understand what I'm saying.
I understand.
If the let's say the diameter of those charges now are very, very small compared to that distance between them, then we call them point masses. Sorry, point charges. The same thing also in molecule. Since we say that the molecules are separated by large distances compared to their own volume, their own individual volumes, that means we can call them point. We consider them to be points. Just as we said point charges, we can also call that one a point mass, that molecules have point masses compared to the what? They are separating distance. Each of them, they are always in constant motion, moving zigzag motion, depending on the pressure or their kinetic energy. Am I making sense?
Yes, I understand now. Thank you, sir.
All right. Is there any other question? Then, if there are no other questions, then this slide will be sent across to you through the, okay, who is it? Issa Ayomide, what's the problem?
So I wanted to ask how you take the attendance, sir.
Attendance, how did they tell you to take attendance? From Zoom here, you can get your attendance. If you request the Zoom to give us the report of this our meeting, okay, it will bring in the whole people that participated. So from there, we know that those that attended.
Okay, sir.
Is that clear now?
Yes, sir.
Adeniro, what was the problem?
Sir, what
Sir,
about
please
those
repeat
that
what you
are
said before.
streaming from YouTube?
Huh?
What about those that are streaming from YouTube?
Those that are streaming from YouTube.
Yeah.
Well, that is not an issue. We know how to go about it. But YouTube too has its own report.
Okay, sir.
The CITS will always give us the download of each meeting here. Everything is being recorded now.
Okay, sir.
All right. So see you next week.
Thank you, sir.
Thank you, sir.
All right.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Okay.